Welcome. This video is going to go over solutions to the Chapter 4 quiz that you had over bonding and structures. So question number 1 is, which molecule has the shortest carbon-oxygen bond length? So what they're expecting you to know, so that you can do this in about a minute, is that when you see this COOH group, we're looking at this kind of bond. So the double bond there is going to be shorter than the single bond. And then when we see the second one, we can assume this is going to be a COH bond, so these two single bonds aren't very long. CO2 you should fairly quickly recognize is containing two double bonds, and it's the CO that contains the triple bond, which is going to make that the shortest carbon-oxygen bond length. Number 3 is asking which particles are responsible for the conduction of electricity in molten aluminum. And what you should know is that the delocalized electrons are responsible for pretty much all the metallic properties we see. So C, electrons, would be our best choice here. Number 4, the electronegativities of 4 different elements are given below. The letters are not their chemical symbols. Based on this information, which statement is correct? So using your table of electronegativities from your chart would be bad information because it may mislead you, because it says only from this chart what can you assume. W is a nonmetal. No, we have no information to support that. W and X form an ionic bond. They only have a difference of 0.3, so that falls in the covalent range. Y is a metal. No, that's highly unlikely. In fact, the whole number is unlikely because 3.4 is pretty high. And then D, Y and Z form a covalent bond. They have a difference of 0.6, so yes, D would be true. Number 5 wants to know which pair of compounds is arranged in the correct order of relative boiling points, with the lower boiling point being on the left, the higher on the right. So A, I've got C, single bonded to an oxygen, single bond to a carbon. And over here, I've got COH, so this would be the lower melting point with dipole-dipole forces, and this having a hydrogen bond. Let's just make sure it's the only one that seems to fit that criteria. The second one, you've got a C bonded to a C, but now you've got HO, so that's letting you know that it's a double bond to the oxygen, whereas on the right side, I've got just a nonpolar 3-carbon structure, so this would be the higher of the two. And then the third one, I've got the 2 carbons again with the OH on the end, so that's going to be a very high melting point. This one, I've got the C and then the H and the double bonded oxygen. So this one is the left side. And then D, I've got C, and then I've got a double bonded oxygen and an OH group. And then on the right side, I've got C, C, and an OH group. So this one would have the higher melting point. Even though they both have hydrogen bonds, this one's got hydrogen bonds and another fairly polar bond. So only A fits the criteria that the one on the left has the lower boiling point. Number 6 wants to know which compound does not form hydrogen bonds. So remember, a hydrogen bond is hydrogen with nitrogen, hydrogen with oxygen, or hydrogen with fluorine. So the OH groups here on the end, those are always a hydrogen bond. That's an alcohol group or a hydroxy group. So C and D both do form them. So those are not our good choices. So it's really between these two. So CH3, NH2, if I think about that, I've got a methyl group with the 3 carbons, and then the end's going to have to be bonded to that with 2 hydrogens attached. So there's another hydrogen bond. So it appears that only B is lacking. And if I look at that, I've got CH, let me try that again. I've got CH3, and then I've got COCH3. So I'm going to have another CH3 group here, leaving the oxygen to be double bonded to that carbon. So with that being the remaining structure, B would be the one that does not form a hydrogen bond. Number 7 wants to know which statement best describes metallic bonding. Remember, metallic bonding is the positive cation with delocalized electrons. So A, oppositely charged ions, no, that's not true for metallic bonding. Electrostatic attractions between a lattice of positive ions and delocalized electrons, yeah, that's what we're talking about, positive ions or cations. C, electrostatic attractions between a lattice of negative ions and delocalized protons, no. And electrostatic attraction between protons and electrons, not quite, because the positive ion actually contains the positive nucleus as well as the inner electrons pulling on just the valence electrons. So this cation is more than just the protons. Number 8 wants to know, Lewis structures are represented in different ways in different parts of the world. 2 ways of drawing the Lewis structure for H3O plus are shown below. And what you should be able to pick up from both of these is that you have 3 hydrogens single bonded to the oxygen, and then you have a lone pair here, represented 2 different ways. So which statement is correct about H3O? The ion has a tetrahedral shape. No, the electron domains have a tetrahedral shape, but the ion itself actually has a trigonal pyramidal shape. The HOH bond is 120. No, that would only be if it was trigonal planar. The HOH bond is 90. No, that's not true even if it was tetrahedral. So D is the only true statement. It has a trigonal pyramidal shape. Number 9 wants to know which species contain a dative bond, dative covalent bond. And at least 2 of them do, possibly all 3. So a coordinate covalent or a dative bond, if you don't remember, is when one species donates both electrons. And if you drew these using the, analog, the method I've shown you, it maybe would have become obvious which 2 of these had similarities and which one didn't. Because when you look at HCHO, if you count up, you have 12 electrons to get everybody happy. So what you end up with is hydrogen bonded to carbon, and then the carbon is bonded to a hydrogen and also another oxygen. So now I've got carbon with its 4 bonds. I have hydrogen with each of its bonds, and I put the 2 lone pair on the oxygen. Nothing unusual about that. Oxygen seems to be sharing 2 and has its other 4, its original 6 valence electrons. Carbon seems to be sharing all 4 of its valence electrons. Hydrogen sharing its 1 valence electron. So if we look at carbon monoxide, now I only have 10 electrons. And when I put this together, I'm going to end up putting a triple bond and a lone pair on oxygen and a lone pair on carbon. Now when we look at this is unusual because carbon has formed 3 bonds, and instead of just having its 1 valence electron left, it's got a lone pair left. And oxygen, after sharing 3 electrons, we should have 3 valence electrons left, but it only has 2 left. So that means one of these bonds is a dative bond where both electrons were donated by the oxygen. With H3O plus, that only has 8 electrons because 1 has been lost. So either the oxygen only has 5 valence electrons, or one of the hydrogens is missing its valence electron. And actually, when we study acid bases, we'll see it's the hydrogen that comes in missing an electron. So what happens with H3O is you have H2O with its 2 lone pair, and then the hydrogen ion comes in and just forms a dative bond with one of those lone pairs to make it H3O plus. So that means 2 and 3 have the dative or coordinate covalent bonds. Number 10 wants to know which has the highest boiling point. A, when you see it's a hydrocarbon, just carbon and hydrogen, hopefully you'll soon recognize that that is just a nonpolar molecule. So that's going to be the lowest for sure. This one, the OH on the end, is our hint that there's a hydrogen bond in there. The HO on the end is the hint that it's a double bonded oxygen to the carbon. So there's a dipole-dipole bond, but that's not as strong as a hydrogen bond. And so the only other possibility is this one with the O in the middle. But when I see a CH3 and a CH3, that means these each have just 1 bond remaining. So the oxygen must be single bonded between them. So again, that's just a dipole-dipole bond. So B is going to have the highest boiling point with the strongest intermolecular forces. Number 11, you just have to know a little bit about carbon and the way it bonds and its allotropes. In C60 fullerene, each carbon atom is covalently bonded to 3 other carbon atoms. That seems true because you have hexagons and pentagons, so there should be 3 carbon branches coming off of each of those. In C60 fullerene, each carbon atom is covalently bonded to 4 other carbon atoms. I don't think so, because that's what makes diamonds unique, is the 4 bonds. In graphite, each carbon is covalently bonded to 4 other carbon atoms. No, again, that's what makes diamonds unique, is the 4 bond. And in graphite, each carbon atom forms a double covalent bond with 3 other carbon atoms. No, that's not true. It can only form single bonds. That would be 6 bonds in an expanded octet, and carbon's not even capable of that. Capable of that only being a period 2 element. So I'm going with A. Fullerene bonds to 3 other carbon atoms. Number 12, these seem to mess with people a little bit, but they're telling you what you need to know. They're just using the symbols A and B, but it says the number of electrons in the valence shell of elements A and B are 6 and 7 respectively. So that means A looks like this, has 2 bonding sites. B has just the 1 bonding site. So what is the formula and type of bonding in a compound formed by these elements? That means I would need 2 B's to get the A satisfied, so I would expect it to be AB2, and it's going to be sharing because it's 2 nonmetals with 6 and 7 electrons, so it's going to be AB2 covalent. Sounds like a blood type. Number 13 wants to know what's the bond angle in the H3O plus ion, and we've seen this a couple times in the tests, so if you don't remember, it's 3 hydrogens and a lone pair, so it's tetrahedral for the electron domain, but the shape is trigonal pyramidal. And trigonal pyramidal means it's going to be slightly less than that 120. It's going to be pushed closer together. So I can expect, or I'm sorry, slightly closer than the 109.5 that the tetrahedral would have. Less than the 109. That's not quite enough crowding from that lone pair. So B, 107 would be our best choice. Number 14, for 2 marks, why does calcium have a higher melting point than potassium? Because its cation is stronger and it has more delocalized electrons. So it has a 2+ charge on the cation versus just a +1 on the sodium. And it has 2 delocalized electrons per cation versus just 1 per cation. Both those things are going to make calcium quite a bit stronger metallic bond and with a higher melting point. Part 2 of that question wants to know why sodium oxide, so Na2O, has a higher melting point than sulfur trioxide. And this is worth 3 marks here, so they're looking for you to say 3 different things. So it's a metallic versus a covalent bond. So that's the terminology that makes them different. That means for the metallic, in the Na2O, you have strong electrostatic forces between your cation and your electrons. But in the SO3, the only thing holding it together are the weak London dispersion forces set up by just temporary dipoles. So these are kind of the 3 different things they were looking for to give you 3 marks. Number 15 for 4 marks wants you to describe the bonding in iron and explain the electrical conductivity and malleability of the metal. So they're going to give you 2 marks for the bonding, and what they expect you to say about the bonding is you might mention it's a metallic bond. That part's kind of irrelevant, but it consists of a positive cation with the sea of electrons, and you could say sea of electrons or delocalized electrons, either one. So those 2 factors are going to create a strong electrostatic attraction. So I wanted you to mention how the bond forms and also mention its strength. So then as far as the electrical conductivity is the easy one to describe. This is because charge can move. And that's because of the delocalized electrons. And then the malleability is a little more involved to explain, but it's still only 1 mark. The malleability is because the cations can be rearranged without breaking the bond. Okay, so I'm going to say cations can be rearranged without disturbing pattern or the lattice, and electrons move easily, and they're what we call non-directional. So they'll go wherever they need to be to help cut down on that repulsion between the cations. Number 16 for 4 marks wants you to explain the boiling point of the hydrides in group 5. Discuss the variation in the boiling point. So for the second 3, or the last 3, you've got a very nice increasing trend here. The unusual part is this really high amount that we see with NH3. So what they want you to know is that NH3 is so unusually high, even though it's the lightest, it's got the strongest intermolecular force because of that hydrogen bond. Okay, so that's going to give you a couple marks right there. And then your other 2 marks are going to be to point out that these 3 all have dipole-dipole forces, so it's not like they don't have strong bonds. So they've got moderately strong bonds, and they're heavier. So we're going to see an increase in boiling point, and the boiling point is going to be, a respectable amount for a covalent compound, but it's going to be less than the one with the hydrogen bond, but we will see the increase because the bonding is similar, but the molecule becomes heavier. Okay, then number 17, I'm going to make some space below to answer these. For number 1, they want you to outline the principles of the valence shell electron pair repulsion theory, or VSEPR as I prefer to call it. And they're looking for 3 things about it. So one thing is that electron domains repel each other. And because they repel each other, they will separate maximum distances. From one another, and lone pair are able to repel more than bonding pair because they do not have 2 nuclei holding them in place. And those 3 factors are really what determines the shape of the different molecules. Number 2 then wants you to use the VSEPR theory to deduce the shape of H3O and C2H4. So you're supposed to draw the Lewis structure. So for H3O, here's the structure, and you include the little plus sign. So the shape is trigonal pyramidal. Notice they really like H3O. That's been on the test about 4 times already. And then the value of the bond angle, because the electron domain would put it at tetrahedral with 109.5 bond angle, it's going to be a little bit less. Typically it's stated as 107, but if you said anything between 106 and 109, they would give you the mark for it. So then with C2H4, let me move this down so you can actually see it. So C2H4, heard several groups discussing that this is linear, but if you've done the practice problems and looked at the solutions, you look at each carbon atom. Each carbon atom is considered a central atom. So this carbon atom has 4 things around it, and this carbon atom has 4 bonding sites around it. So this is considered a tetrahedral shape from the perspective of each carbon separately. And each carbon is going to have 4 things attached to it with that 109.5 degree angle, which is another reason it has to be tetrahedral rather than linear. This is not going to be a 2-dimensional flat thing. So number 3, predict and explain whether each species is polar. Let me squeeze this in here. H3O plus, definitely polar. You've got 3 hydrogen bonds going on there and a lone pair. C2H4, even though it's not linear, it's tetrahedral, so that is definitely nonpolar. And then number 4, using table 7 of the data booklet, predict and explain which of the bonds, OH, ON, or NH, would be most polar. Well, they directed you right to the data booklet, and all you had to do was do some subtracting, and you should have found that OH has the greatest difference in electronegativity, making it the most polar.